Good morning. In this talk, I'm going to talk about how to automatically recover from an attack in interconnected web services. Today's web services are highly interconnected. It means many web services provide APIs, and many other websites integrate those APIs to provide their own service. For example, for authentication, they're using Facebook Connect or Google Plus-like system. For data sharing, they're using Dropbox-like storage system. As one example, say we are running online shopping mall. Because we don't want to develop everything from scratch, we integrate our online shopping mall with existing website, such as Financial Force for accounting service and Bill On service for invoice and billing services, and similarly for e-signature. These days, many people seem to like social network, so we integrate with our online shopping mall with Facebook and Twitter. It means that users in Facebook can purchase our product online without any further registration. For example, when users buy a product online, we're going to create an invoice with the user's address in Facebook account. This integration seems great to me, but what if there is a bug in one of the services? What if there is a bug in Facebook so that the attacker can modify users' data in Facebook? For example, attacker modify users' address in Facebook. Then when user buy a product, we're going to create an invoice with the address that was modified by attacker. This attack scenario is not very far from the real world because there are tons of vulnerability in web service out there. For example, a few months ago, the Break security guy found a vulnerability in Facebook Connect. Because of this vulnerability, attacker can intercept fully permission access token of the user. Other major websites were not the exception. For example, in Twitter, Instagram, and Yammer had a similar vulnerability. The goal of our project is to recover integrity in interconnected services. It means we want to repair the state of the affected services as if the attack never occurred at the first place. However, what we can do at best in current system is just manual recovery, because administrator of one site never trusts the other sites for recovery. And also, manual recovery requires interaction between multiple administrators. Our approach for this particular problem is as follows. We're first going to use rollback and replay for recovering integrity within single machine based on our prior work. And we're going to extend the rollback and replay to many web services. However, there are a couple of interesting challenges in doing so. First, rollback and replay of many websites require a global coordinator who understands entire pictures of an attack, because each service cannot decide what to do for recovery. Also, we carefully re-execute every single request in the picture. All services must be available during recovery. However, we want to repair some services even if others are offline. Because we repair some part of the system, the consistency problem arises because some services are not repaired yet. Contribution of our work as follows. We could enable automatic intrusion recovery in distributed web services. In order to do this, we first define repair protocol between services, which doesn't require any central coordinator. Secondly, we support asynchronous repair, and it means we can proceed our recovery even with unavailable services. Before going further, let me simplify these running examples of an attack. We're going to keep only interesting parties in this attack, including Facebook and online shopping malls and Bill On service. In order to make this running example complete, we're going to introduce a victim users in our picture. And this victim user click this URL crafted by the attacker user. And when victim user click this URL, it will initiate the authentication to the Facebook. And Facebook has the vulnerability. Facebook will return an access token to the attacker. And by using this access token, attacker modify user's address in Facebook account. Then when user buy a product online, we're going to create an invoice with the address that was modified by attacker. Let me represent this attack scenario with timeline graph. There are 5 different parties involved in this attack, including attacker, victims, and Facebook plays as a role of authenticator and also content provider at the same time. And 2 other services, the shopping mall and bill-on service, simply contact to the Facebook. We're going to represent each operation based on downward timeline. First, victim initiate authentication to the Facebook. Because we have vulnerability in Facebook, we're going to return the access token to attacker. By using this access token, attacker modify user's address in Facebook. And when shopping mall fetch address of the user, it will get the attacker's address and push this attacker's request to the bill-on service. Before we actually recover from this attack, let's think about what is correct state to recover. It means what if attack did not take place at the first place? When victim user initiate authentication to the Facebook, because we don't have vulnerability at this moment, we simply return the access token to the user. And when shopping mall contact the Facebook, it will get the correct victim user's address. And similarly for bill-on service. We think this is the ideal state after successful recovery. Then how our system work? This is the overview of our system execution. We have 2 different phases of execution. Normal executions and repair. In normal execution, we're going to record enough information for rollback and replay. And the repair time, we're first going to identify an attack to initiate the repair. And then we're going to repair our local state by rollbacking the state right before the attack was introduced. And we're going to replay the recorded request after that. Now, whenever our local repair modify the request that affect other requests, other services, we simply propagate this repair to other web services. Let me talk about this repair process in more detail. This is Strawman design of our repair mechanism with a global coordinator by using rollback and replay. In order to initiate this recovery, we need to identify an attack for repair. In this example, all the requests that was modified, that was affected by this vulnerability in Facebook will be re-executed. In order to roll back our system, we simply stop the entire work and roll back the Facebook, including 2 other services. Then we're going to re-execute the recorded request. For example, when we re-execute the authentication request by victim user, we simply return error to the victim. And then when we re-executing update request by attacker, because we didn't authorize this access token at this moment, we simply return error to the attacker. And similarly, when we are re-executing requests by shopping mall, we're going to return the original victim's address to the shopping mall, and similarly to the bill-on service. Then after this recovery, in Facebook, we're going to remove the access token of the attacker user. In 2 other services, simply got the original victim's address. However, there are 2 interesting problems in Strawman design. First of all, because we carefully re-execute every request in our attacker picture, all services must be available. And also, rollback and replay of entire websites require a global coordinator that understands entire pictures of an attack. Let me talk about this problem first. The first challenge that we're going to talk about is that we need to cooperate with unavailable web services because 2 other services can be offline or simply unavailable during recovery. So it means that the unavailability in single website can prevent the recovery of other websites. Our solution for this particular problem is that we simply support asynchronous repair. It means we asynchronously deliver repair requests, and we speculatively proceed local repair with our past responses. And after our local repair, we simply expose our internal state to the outside world. Our intuition behind this asynchronous repair is as follows. The many websites are designed for independent operation. It means many websites is already prepared for handling failures of many other websites. So it means this is natural fit for asynchronous repair. Let me show you an example of asynchronous repair. In this example, instead of rollbacking many other websites together, we simply roll back the state of the Facebook because Facebook had the vulnerability. And then we asynchronously repair the state of the Facebook. In this case, we speculatively proceed with the past request by shopping mall and asynchronously deliver new response that we modified it, which contains the original victim's address. Then when shopping mall got this new response from Facebook, it similarly roll back its system state and asynchronously repair. One main difference between this design compared to the prior one is that we simply expose our internal state right after our local recovery. It means that if another web service contacts the Facebook after our local repair, we simply return the repair victim's address, even though other websites are still repairing their state. Then, what if speculation fails after we exposing our internal state? It means what if services respond differently? Then we simply restart our local repair with the new response that we just got. In fact, this is not very different from initiating new repair. What we are arguing here is that asynchronous repair will converge to the correctly repaired state at the end. Let me show you an example of speculation fail. So when we got this attacker's update from Facebook, attacker's address from Facebook, let's say we are sending a message to the Facebook that contains this message. Whenever our product is ready, it notifies to the Facebook with the attacker's address in it. It means there is a data dependency between previous request and this message. Let's say we are asynchronous repair this Facebook. One thing to note that is we correctly recover the first request. However, when we are re-executing the second request, the message still contains the attacker's address in it. So when shopping mall got this first message and create new message that contains the victim's user's address. And it means that our speculation failed in Facebook side. In this case, we simply roll back our system state right before the new request by shopping mall, and similarly re-execute with the message that we just got. What we are arguing here is that asynchronous repair makes forward progress in timeline graph, so it will converge to the correctly repaired state at the end. So another topic that we're going to talk about is the consistency problem. Because we expose our internal state right after our local repair, user might see two different states. One is repair state, another is the state that affected by the attacker, because two other services are still repairing their state. However, this is not something new that our recovery mechanism introduced more, and also most of the web services already cope with this problem. However, in some cases, exposing partially repaired state might violate service invariant. Service invariant means an application-specific guarantee by service provider. For one example, in the locking service, they guarantee that when lock is held, no concurrent access is allowed. So in theory, exposing partially repaired state might violate service invariant, particularly in tightly coupled system. But in practice, exposing partially repaired state might be just okay, because RESTful API usually provide consistency per API, and also web services are natural, usually coupled. Then how can you reason about partially repair consistency? First of all, services and clients already deal with concurrency. It means that multiple clients can access the service independently. Then we're going to model the repair of a service as a list of invocation of a regular API. It means there is an imaginary repair actor client that invoke regular API to fix the problem. So the partially repaired state can be considered as a state resulting from yet another concurrent operation by repair actor client. Let me switch the gear and talk about second problem in Strawman design. In order to roll back the entire website, we need a global coordinator that understands the pictures, attacker's pictures in their history. But how can we remove this global coordinator from our design? In other words, how to propagate this repair request without any global coordinator? Because we don't have any global coordinator, we need somehow uniquely name this request such that multiple websites understand correctly. In order to do this, we assign an identifier to each request in normal execution. And each service for recovery, they running a repair controller. I mean, in order to initiate a recovery, we simply contact to the repair controller of target website. For one example, when shopping mall send request to Facebook, we're gonna assign identifier to that request. If Facebook want to modify the response, Facebook have to invoke this API called replace response API in the repair controller of the shopping mall, including unique identifier and the new response that Facebook want to modify. In fact, we provide 4 different kinds of repair API, which doesn't require any centralized coordinator. It means each service invoke following repair API to recover from the attack. Each website can modify the request and response, and even delete the request in the past. If they want to create a request against the history, you can simply invoke create API. What we are arguing here is that if services support those 4 APIs, it can participate in decentralized recovery. I mean, if your website has vulnerability, you can actually help other people to recover from the attack. We now have a list of repair API, then who can actually invoke this repair API? In fact, authentication of repair API is too application specific. For example, thinking about email service, do I have to allow the sender to delete the recipient's email? It's probably not, because your email suddenly disappear from your inbox. It might be surprised. In order to avoid this problem, we simply delegate the authentication to the original website. So each application can implement their own policy. For one example, application asks administrator for confirmation of repair. In order to keep track of authenticated repair requests, we assign a credential to the repair request. This is a quick summary of our design. We first support asynchronous repair so that we can proceed our repair even with unavailable web services. We define repair API between services, which doesn't require any central coordinator. We implement this idea as a prototype called Aire. We implement Aire by extending Django Web Framework. So we could support existing Django application with just few modifications. For one example, the application-specific authentication policy of one of the largest application, we actually require to modify about 50 lines of code. We evaluate our implementation by asking 3 questions. Can Aire support your web services? Can Aire recover from distributed attacks? And lastly, what are the runtime overhead of Aire? First, Aire support your web services. In order to demonstrate this, we ported the existing Django application to run on Aire, including Askbot and OAuth provider in the past. Askbot is a forum site that user can ask questions, which is similar to the Stack Overflow. When user requests sign in to the Askbot, it will initiate OAuth authentication between Askbot and OAuth provider that we implement. After registration and login, user can write a posting. If the question contains a code section in it, it can the Askbot share the code section with the deepest service so that the users in Askbot can easily share their code section among them. In fact, this is not the toy example. Combining them all, it consists of about 180,000 lines of code. It means that Aire can actually support large Django web application. We also check if Aire could support automatic recovery. In order to show this, we introduced a vulnerability in OAuth provider, which is a similar vulnerability to Facebook Connect. By exploiting this vulnerability, attacker got the fully permission access token of the user and propagate through the services by posting a question that contained the code section. In fact, this synthetic example seems to be very naive, but think about it. What if there is a vulnerability in deep past when highlighting this source code? Then attacker, by exploiting this channel, attacker can propagate the deep past service. After we introduce this attacker, we initiate the automatic recovery from OAuth provider. And then we check if we could remove the access token of the attacker in OAuth provider. And we check if Askbot successfully removed the posting by attacker, and similarly in deep past. As a result, we could successfully remove those attacks from our services, even if deep past is temporarily unavailable, even if deep past goes offline. In fact, there are more examples in our paper, including intrusion recovery and mistakes on echo setting and misconfigured versioning spreadsheet. We also checked the runtime overhead of Aire. Aire imposes about 20 to 30% throughput overhead and 10 kilobytes per request storage overhead. It means probably for high-performance web services, Aire might be not good fit for them, but for websites which care integrity more than performance, we think the Aire imposes moderate overhead for them. We also check if Aire's repair is efficient. For the experiment, we introduced attacker in our previous pictures, and attacker log in as victim users and write a posting. And after that, 100 legitimate users post 5 questions independently and navigate through the forum. Then all users are affected by the request, affected by the attack, because they all read the attacker's posting. In order to recover from this attack, we initiate the automatic recovery from OAuth provider and check if we can propagate this repair to Askbot and deep pass accordingly. Quantitatively, we needed to re-execute about 5% of total requests. In terms of repair time, our repair time takes about 2 times shorter than the normal execution, although re-executing a single request for recovery takes 10 times slower than the normal execution, because for every time we access the database, we need extra communication between repair controller and the original web. There are 2 branches of related work in intrusion recovery with selective re-execution. They are retro and warp. In fact, we use them as a building block for asynchronous repair. It means by using the selective re-execution idea of both projects, we repair a integrity within single machine. In the distributed setting, there are hit rate, polygraph, and Aire. But in Aire, we could enable automatic intrusion recovery in rather loosely coupled websites. In summary, we introduced Aire, which recovers integrity of distributed web services. In order to do this, we define a repair protocol, and we support asynchronous and decentralized repair. And then lastly, we proposed consistency of partially repaired state. Thank you.
Can look at the questions. Questions? Yes.
Hi there. My name's Brad Chen, and I work for Google. And I really like the direction you're looking at with this work. I think it's, an important problem, great to work on. But there's some aspects of what you've described that seemed kind of removed from reality as far as the version of it that I work with. One example is side effects. It really depends tremendously on how quickly you detect the problem. If you detect it within minutes, then maybe a lot of this stuff might have a chance of working. But suppose it took a day or 2 or 3 days. The product could already be delivered. The money could already be debited from an account. And even apart from these, obvious material side effects, there's also computing side effects that are happening all along the way. The talk sort of suggested that these systems are flat and simple, like you have one thing, you correct it, and you're done. But the fact of the matter is when a transaction of this sort happens, first one system commits, but then there's a whole tree of downstream systems, and all of those need to be corrected as well. So that's one kind of, the side effects question is one kind of difficulty that I'd encourage you to maybe comment now or explore in future work. And I'll leave it at that because I see there's other questions.
Thank you for the question. This actually raised pretty good problem in our work. The thing is, actually answer can be twofold. For the detecting attacks in our history, there's another work that we did, like called Poirot. that given the patch of your modification of your source code, actually you can find some attack that in order to initiate the recovery from this moment, this work. Second, your question might be, in fact, we are thinking about this recovery in rather loosely coupled website. We're not arguing that our system actually supports very tightly coupled systems, but somehow, what we are arguing here is that if your system has the intention to support asynchronous repair, if your system provides 4 different API that we suggest, you can somehow participate in this recovery. Our current solution of this work is that we are assuming that all services out there using our repair things. But if you have something that, because you have much more high-level semantic in your application, that how to organize for this API to recover from the attack if you have requests by other services.
Just a couple other things to think about, and again, I don't want to discourage you, but
let's
scale.
take another question, please. Don't leave this offline. So I have, I feel like dear Abby here. What if the repair API is attacked? It now has the ability to code change history, replace past requests and responses, add and remove log entries. Is there a repair API?
Short answer is yes, because you can repair the previous history and including the repair state after that. But for that particular problem, this is why we introduced the delegation of authentication to the application, because allowing sender or request sender to initiate the repair might be not a good solution for many applications. By default, we can allow every sender to initiate the repair. For now, our solution is to simply delegate this mechanism to the original web developer.
Let's take another question.
So I was wondering I'm Jose Falero from Yale University. I was wondering if you guys had looked at sort of checkpointing a state that you know that is safe and sort of getting rid of old log entries so as to, get rid of garbage.
Oh.
Have you looked at that direction at all?
I think this seems to be interesting direction. What we are actually doing is quite the opposite direction, right? Whether instead of removing out the garbage state in our system, we simply create the legitimate state after the attack. So it might be a good direction to think about.
Okay, thank you.
Thank you very much.